So in the last lecture we talked about the law of small numbers and how the Poisson distribution arrives naturally when we analyze sums of Bernoulli random variables with very small success probabilities. So it's very interesting to analyze this when we consider time as what the Bernoulli random variables appear within. So we can think of the Bernoulli random variables as a bag of coins. So we have several coins and we throw them up and we count how many heads we have. Very small probability coins together will generate a Poisson random variable. But it's very interesting to analyze what happens if we toss one of these coins at a time. So this would give rise to Poisson point process. On R. So analyzing something very similar to what we saw in the last class, but instead of looking at a binomial random variable NP, which can be understood as a bag full of coins that you toss all of them at the same time, you think of it as something happening. So let's put our plus here to give even more of a time passing feeling. So imagine that now each coin is being tossed over time and sometimes you have a success. So it's very related to the previous problem, but it has this time component. And to motivate the definitions we have below, we imagine a strange situation. Imagine we have a tenant that is trying to audit some employee. Okay, so this is the boss and this is the employee. And the employee would like to sleep whenever possible, while the boss would like to keep the employee from sleeping. So what the boss can decide to do is just a sequence of times t0, t1, t2 when it will observe the employee. And what the employee can do is to decide when and whether to sleep based on these observations of visits from the boss. So let's do a few observations. So first, if Ti is just I, which is an interesting visiting pattern, the boss will be visiting the employee every hour, for example. So it's very easy, if the employee knows this pattern, it's very easy for him to sleep in the intervals between visits. So just put a small margin there to be safe, and you get to sleep almost all the time. So this is not a good strategy. A second possibility would be to have TIs be random. Okay, this already makes the employee life more complicated. But what if the TIs satisfy Ti plus 1 minus Ti larger or equal than A almost surely? What does it mean? That the times are random for visits, but whenever you have a time, you know that within some interval A, you're not going to revisit. So this scenario makes it possible for the employee to sleep a little bit after each visit, because he knows that there will be no visit in the next 8 steps. So we'd like to have these inter-arrivals be more uncertain to the employee. Okay, so the first intuition we have from this, so let's imagine now, since they are random, that they are denoted by uppercase T. So you have T1, T2, and so on and so forth. These are the visits. And we would like that the visits T1 and T2, for example, up to Tk, they give no interesting information for the employee whether the next visits will occur soon or not. So how do we make this statement rigorous? So we would like to know the probability given that we make a visit at time little tk. What's the probability that the next visit tk plus 1 and the others tk plus 2 sorry, this is too much to hope for, right? We know that the next visit is going to be after the previous visit, but what if we subtract the previous visit? So we look at time, here, and we know that at tk there was a visit. So what if the process had just started here? We don't know anything of what happened, we just start afresh. So this would say that tk plus 1, which is somewhere here, minus tk, so this difference, and then tk plus 2 minus tk, and so on. Any event for this remainder of the process should have the same distribution as the original process, t1, t2, and so on. So this is a formal way to say that after time, if we know that there was a visit at time tk, then this process that starts here and considers this as the new zero, this process is the same as the original process. So this is interesting because it says somehow that knowing the information for the last visit doesn't add anything to the employee. So if this is true, this equality, let us look at the probability that something happens in the first visit, and then the interval between the second visit and the first visit also satisfies something. So we want to know an event that includes some information about the first visit and some information about the interval between the first and the second. So this, of course, can be written as the expectation of the indicator T1 in A, and then T2 minus T1 in A. But now why are we putting this in terms of expectations? Because then we can put the conditional expectation inside. And we want to put the conditional expectation given Tk here, T1, sorry, because then this will go out, and here we have the indicator that T2 minus T1 belongs to A2. So we did nothing, we just wrote it in terms of expectations and included the conditional expectation inside. So why is this interesting? This is starting to look like what we have above here. Here we have T2 minus T2 minus T1, and we are conditioning on T1. So another way to write this is indicator T1 belongs to A, T2 minus little t1 given t1 equals little t1. So some of you may not have seen what this and I forgot here. This should be composed with t1. So some of you may not have seen this. What I'm saying is, since this expectation inside is measurable with respect to t1, we can always write it as a function composed with t1, and this function is denoted as such. And the substitution principle says that when you do this, you can replace every occurrence of T1 by the variable that's going to be replaced by uppercase T1. So this is not very complicated. It's part of probability 1, so to speak. And the advantage of writing it like this is that here we have exactly what we wrote here. You see, we know that this has the distribution of T2. So this is the expectation. Here we keep the indicator of T1 in A1. And here we have the probability of T1 belonging to A2. So here you see that T2 minus T1 belonging to A2, given T1 is TK is T1, is equal to probability that T1 is equal to A. It belongs to A1. And this is just a product. Sorry. T1 in A1, T1 in A2. So here there are two interesting things to observe. First is that we are saying what the distribution of this is. So T2 minus T1 has distribution T1. Why is this? Because if A is the whole space, here we get only this, and here we get 1. So T2 minus T1 has the same distribution as T1. So actually we could write this as such. And another thing we are learning is that they are independent. T1 is independent of T2 minus T1. So reasoning in an analogous way, we see that all this family here is independent. And it makes a lot of sense then to define, for example, T0 equals 0, so that we can write here minus T0, and define all this to be x. So x1, x2, x3, and so on. So if we go back to our picture, we had here the visits of the boss, T1, T2, T3, and so on. And the times between visits, we call them x. And this is a bijection in the following sense. So the space M T of all the T1, T0s, T0 equals 0, T1, T2, and so on, is going to be equal after some bijection to the space of x1, x2, and so on. But we have to be a bit careful here because we don't want blow-ups, right? We don't want to have an accumulation of visits in finite time. So this is going to be the space, given that the size of the set Ti such that Ti smaller or equal than L is finite for every L. So what we are saying is that is a sequence of points that are increasing, strictly increasing, and between 0 and big L there are only finitely many points Ti. And analogously, we can define here what these x's have to satisfy. They have to satisfy that the sum for j equals 1 to I of xi smaller or equal than L. So the I such that this is smaller than L is finite for every L. So it's very similar, and this already gives us the intuition of what the bijection is going to be. So we're going to take an application lambda that takes T1, T2, and so on, and it's going to send to T1 minus T0, or T1 minus 0, T2 minus T1, and so on. It's a bijection from MT to MX. So what this means, this is a B measurable bijection. So we can represent this process using the T notation, like here, or using the X notation, like here, interchangeably. This doesn't make any difference. We can go from one to the other. The advantage of representing it as T is because you can see in the line the arrivals. The advantage of representing as X is because, as we saw in the above calculation, the inter-arrivals in this context that we want to make the process very unpredictable, they will be independent. So it's very convenient to have an ID sequence. So another interesting observation is, if we want to give as little information as possible to the employee, then we'd like to say that given that T1 is larger than T, so the employee is waiting and hopefully working, and when he knows that the boss has not arrived before time T. So time is like here, and in this time the boss has not arrived. What's the probability that the boss will arrive at some next interval? So T1 minus T belongs to A. So we would like to give very little information from this time to this. So if the employee was feeling observed in this time, we would like the employee to feel equally observed in this time. We wouldn't like to have something that becomes easier and easier for the employee to relax, or harder either. We don't want to have this distinction. So we'd like this distribution to be the same as the distribution of that T1 belongs to A. So in other words, if you know that there is no visit until time T, and you call this the new zero, and look at the process from here on, we would like to see the same process again. And this equality here is what we call the memorylessness of the random variable T, and we know the exponential lambda random variables, they satisfy this. So we have a very good candidate for our process, which is just take x1, x2, and so on, be IID, with xi distributed as an exponential lambda random variable, and define the ti's being the sum, for I until n minus 1 until n of xi. So this is our intuition, given that we want this process to be very unpredictable for the employee. This is our intuition of how to define it. And now what we're going to do is to formalize a little bit more this definition, give another representation, because we have a representation in terms of times and in terms of inter-arrivals. We're going to give a third representation that's also going to be in bijection with the other ones. And then we're going to prove some properties of this process that will relate to the Poissonization that we talked before. So before we have to introduce some more notation, so let D 0 infinity be the space of all CAD-lag functions, I don't know if you already saw this definition. So a function is cadlag if it's continuous to the right and has a limit to the left. In French, it's continue à droite, a limite à gauche. So we have functions like this, for example. And by the way, from 0 infinity to say n. So we have here the natural numbers, and this function starts at 0 here, times 0, and it can jump because it doesn't need to be continuous, but for every time that if it's continuous, it's fine because it's going to have a limit to the left and be continuous to the right. But at points where it may be discontinuous, it has to be continuous to the right, like in this picture, and it needs a limit to the left. So that's the space of cadlag functions, and it's a very nice space. It's a great replacement for the space of continuous functions when we actually want to allow for jumps. This is the right way to do it. And what we want to use this is to represent these arrival times in a different fashion in terms of a random function. So for this we define another map that will take all our times x, so it will go from mx to the space of cadlag functions. And what it does is it takes a family x0, x1, x2 of inter-arrivals and returns a random function n t. So n is an element of the space of cadlag functions, where n evaluated at time t is the maximum number of n's such that we have no more than n arrivals until time t. So you remember that the space mx requested this to be finite for every L that we put here. So this maximum is gonna be attained. So if we have here the line, let us make a picture of what this function n looks like. So we have the inter-arrivals x1, x2, x3 here, and you see if we take t equals 0, even if we have only one term in the sum, it's already bigger than 0. So this is going to be 0 at 0. Actually, if time is smaller than x1, this is impossible this cannot happen. So this is also going to be 0 until time x1. At time x1, it's already possible to put n equals 1 here, and the sum is going to be just x1, it's smaller or equal than x1. So here we jump from 0 to 1. And here we go, and we jump from 1 to 2, and we jump from 2 to 3, and so on. So what this process does is it counts the number of arrivals until time t. So if you look back here, now it makes more sense. I'm looking at a time t and I want to know the maximum number of arrivals that fit until time t. I cannot count an arrival that the sum will jump over t. For example, if this is t and this is x4, I don't want to count x4, I don't want to put 4 here because the sum would go over t. And again, this process NT, if we restrict a little bit the space of Cadeias functions to be only increasing by ones and not exploding, it will be by injection through this gamma to the spaces both M, X and MT. But I don't want to go through that. Gamma is enough for us. It's enough that we know how to translate X's to D. Don't want to go back. We're not going to need to go back from D to X. But the important thing to observe is that we already have everything set to introduce the definition we want. So we want to define the process N that is coming from the motivation we did before. And we're going to call it the Poisson point process. On R with rate lambda is the distribution on the space of Cadeias functions given by so we take exponential random variables for the interarrivals with parameter lambda. We take infinitely many of them to one for each x and in an IID way, so this is a product, so it's IID, and we look at what is the distribution of in gamma given by the push forward of this. So one way to write is like this, but the one we are using more in the course is this, right? So we want to define a distribution on the space of Cadeias functions. We take the pre-image and measure on the space mx with a product of exponentials. So this is going to give us a process that looks like this, and each interval like this is distributed as an independent exponential with parameter lambda. So this is the definition of a Poisson point process on the real line. And of course, after we have this, we can define Tk, Tn to be the sum of xi. So we can write here T1, T2, and so on. Sorry, T3. And this process that we have defined is called Poisson for a reason. So what we're going to do now is to look at the relation between this and the Poisson distribution that we talked in the last class. And this comes through this lemma. I'm going to give two motivations for the fact that this is called Poisson point process. The first is this lemma that says if you fix lambda bigger than 0 and take some fixed time, then the random variable nt, so n was a process right here, that's a Poisson point process, is a process here, but nt given of time t is a random variable, and this random variable has distribution Poisson lambda t. So this is what relates the above definition with the random variable, the Poisson distribution that we talked in the last class. So the proof is going to be simple, but it's a very nice application to exercise conditional expectations. So the first step is to show that for every t, the probability that nt is equal to 0 is the probability that Poisson lambda t is 0, which is exactly this. So this is what we want to show first. But what's the probability that the number of arrivals until time t is 0? So this is equal to the probability that the first visit was after time t. Because if the first visit comes after t, there was no visit until time t. And if there was no visit until time t, the first visit. So it's a bijection. And this, since this is an exponential random variable with parameter lambda, is exactly what I mentioned. Okay, so step 1 was easy. The step 2 is to take care of the remaining values of the distribution nt, and you do this by induction. So suppose that for every t, the probability that nt is equal to k minus 1 is the probability that a Poisson lambda t is equal to k minus 1. So we have assumed that we have proved for k minus 1 and for every t this equality. Now consider the case k. So you see that here we proved for every k, right? So it was important to prove for every k because here we are taking for every k in our induction hypothesis. So what we're going to do is a shift that's very similar to what we've been talking about when we motivated the construction. So if you didn't get much of this motivation here, you can ignore it because it's informal. So up to this definition here, all I spoke, it was an informal description. Now we are really proving something, so we cannot be very sloppy here, we have to be more careful. So we have here x1, then x2, and so on. And what we want to do is exactly do the shift that we informally described before. We want to fix some time t, and we want to actually the best picture would be this. We have some time t here. We want to first have one arrival before time t, because here k is already bigger or equal to 1, right? We already treated the case 0. So we have one arrival here, and we want to look at this process from this point on as if it was the original process. So we're going to make something similar to what we did before, but now in a more rigorous way. And the first observation is that this can be done in the deterministic function gamma, without talking about the distribution yet, in the following sense. So the function n that is associated to a sequence of points, when we evaluate it at R, can be related to the same function if we subtract R here, if you subtract S here, in the point R minus S, if x1 is bigger than s. So what am I talking about here? So imagine that we have some time s here, and we know that the first visit arrived after time s, just like in this picture. And forget t for a moment, we're going to talk about t soon, but this is more general. This for every r and for every s. Imagine that the first visit arrived after s, and we are looking at the process on some time, the counting process, right, at some time r. So what we can do is we shave off a bit the x1. We consider x1 to be just this reminder here. We don't change x2 or any other, But instead of looking at the whole interval R, like we did here, we look at the interval R minus S, which is this distance here. So you get the same height. If you consider the process that starts with x1, x2, and so on until time R, and x1 happens to be bigger than S, then we can shift and look at not until R but until time R minus S and remove this S from x1. So this is a deterministic observation. There is no conditional probability or anything here. Now we are going to use this observation to do something that involves conditional probabilities. And it's exactly how we are going to calculate the probability that nt is equal to k. Right? We already know the probability that nt is equal to k minus 1. And you're going to look at the probability that nt is equals k. So, okay. We know that if nt equals k, then x1 has to be smaller or equal than t. Right? Because if x1 is bigger than t, and t is 0, and k is bigger than 0. So we can include here x1 smaller or equal to t, and don't change anything. Now, another thing we can do is to write nt as gamma of something, right? Gamma of x1, x2. This is nt. If we evaluate this at time t, we know that this is k. Okay, so I did nothing here. I introduced an event that contains the left event, so this doesn't change, and I rewrote this event in terms of the gamma function. But now this allows us to look at the process here in the line. So there's some time t, and x1 happened before, and we are counting the arrivals, and at time t we have k arrivals. So that's the event we are looking at. And by just using something completely deterministic, which is this lemma here, we can look at this between x1 and t instead of 0 and t. So what do I mean by this? We can write this as the expectation. We keep this x1. By the way, let's go even slower. We can write this as the probability that x1 is more equal than t. And now this event here on the x1 is more equal to t, so can be written as gamma of x2, x3, and so on at time t minus x1 is equal to k minus 1. So let's look at why this is true. This is actually an equality between this event and this event. So we were counting how many arrivals we had between 0 and t, and we realized it was k, right? K is the number of arrivals until time t. But we also know that the first arrival happened here before. So if we look at the process from here on, this is the process gamma x2, x3, and so on. But starting here, we have to move not only the time, our 0 time here, but also our y-axis. So if here was the 0 before, now we have to move both the time to x1 and the number of arrivals one step up. So this is our new axis. And the process that you see here, the process that you see here, that stays here and then it jumps, here is x1 plus x2, but in the new axis it's just x2. This new process, it's arriving in height k minus 1. after time t minus x1. So if you look at this picture, we just shifted a time by x1 and we shifted y-axis by 1, and this is exactly what we get. But we can completely forget the x1 here. We're counting from x1. So now we can take conditional expectations with respect to x1, and it's measurable, so this goes out of the conditional expectation. But here we have a gamma of x2 and so on at t minus x1 being equal to k minus 1 given x1. So just conditioned on x1, and as we did before, we can use the substitution principle and write this as little x1 given that x1 is equal to little x1, and compose this with x1, and here what we have is, okay, this has the same distribution, so this is looking at variables that are independent of x1. So actually this gamma here is independent of the conditioning. It's not going to look at the conditioning at all. And the probability that gamma of some time is equal to k minus 1, this is the probability that n t minus little x1 is equal to k minus 1. And by induction we know that this is the probability that the Poisson lambda t minus x1 is equal to k minus 1. So this, what's inside, is completely independent from x1 except for the parameter here. So we're going to take this function here and compose it with x1. So we're going to get the same indicator. And here we have the probability that a Poisson random variable with parameters lambda times t minus big x1 is equal to k minus 1. So this may look strange for you because we are looking at the Poisson random variable that has a parameter that's a random variable, but this is nothing strange, right? We did this several times. For example, you can take a uniform random variable 0, 1 and use the result to toss a coin that's Bernoulli with parameter u. So this is something that we do often. We use a random variable as the parameter to another random variable. And now what we do is just replace by the known distribution of the Poisson. So the distribution of the Poisson is, okay, we have to use the fact that this is the strange parameter, but we put the parameter to the power k minus 1, e to the minus the parameter, over k minus 1 factorial. And this can be written as an integral. Now we only have x1 here. So this is an integral with respect to the distribution of x1, which is this. There's a lambda to normalize. And t is not a good variable for integrating x1. Let's call it x. So we are integrating this. We can even call x1. We are integrating under this distribution this function here. So the indicator can be just turned into the integration limits. And here we have lambda t minus little x1 to the k minus 1, e to the minus lambda t minus x1 over k minus 1 factorial. And now you see that the exponential of minus x1 is going to cancel this, and we have an integral that is very classical. You can do it yourself, but you're going to end up with lambda. So this lambda to the k, this lambda here is to the k minus 1. It's going to join with this lambda. It's going to become lambda to the k. This exponential is going to be exponential of minus lambda t, because the x1 part will cancel with this part. And the integral of a polynomial, you just do the thing, and you know that you can calculate and see that it's t to the k. So here we have, t to the k over k. And here we had k minus 1 factorial. And you can join the lambda and the t. We can take the exponential out. And we can join these two to get k factorial, which is the distribution of a Poisson. Probability that a Poisson takes value k. So this is finished the proof that the number of arrivals until time t in a Poisson point process is a Poisson random variable with parameter lambda t. This is the first link between Poisson and Poisson point process, Poisson distribution and Poisson point process. And I'll leave with you an exercise which is to think about the discretization of this process. So imagine that we have here visits from the boss to the employee that can only happen in discrete times, let's say every minute. And what the employee does inside this minute here is not really relevant. The employee cannot sleep between one visit and another if they are right adjacent to each other. So this minute is very refined in a way. And imagine that the boss decides to toss a coin. So the fact that this interval is very small is going to be represented by the fact that we call this 1 over n. So we can take n to infinity and make this interval very small. And the boss will toss a coin here, y1, y2, y3. The yi's, they are IID, Bernoulli random variables with parameter lambda over n. So of course n has to be larger than lambda, otherwise this doesn't make sense. But this is how the boss will decide when to visit. It will toss a coin every minute, and and all these coins have very small probability, but if it has a success, then it does a visit. Whenever you have a success, you go see the employee. Now, what's the distribution of the first visit? The first visit we are going to call as before x1, and this, you can see the distribution is just a geometric with parameter lambda over n divided by n. So the geometric would be something that takes value in integers, but since we are dividing time by n, so this has the distribution of a geometric divided by n. And this is the exercise. Show that this converges to, so weakly, to an exponential lambda random variable. So indeed, if we refine this, we get exactly the exponential distribution of the first arrival. Also x2, which is the time between the first and the second visit, is of course going to be independent of the first one, and it's going to be in the limit distributed as an exponential as well. So this is something that you can prove as well, the independence of the xi's and the fact that they jointly converge to independent exponentials. And another funny observation is, if we count for a fixed time t how many visits there were in this interval, this is of course going to be, so the number of visits that we of course call NT. These will have distribution binomial n because NT, because until time t we have n times t intervals of size 1 over n, and the success probability is going to be lambda over n. And if you plug this into what we have seen in the last class, you see that this converges to a Poisson lambda n, because we just take the product of these two and it's going to be, lambda t. It's going to be lambda t. So the exercise is to show this convergence here and the fact that the xi's are independent, to see that the Poisson process can be seen as the continuous process above, but also as the limit of this discrete process here. Okay, so in the last class we're going to leave the real line and go to Poisson process in more general spaces. To see you.